Hey everybody, this is 5B impulse. So it says two different boxes are pushed from rest on a frictionless surface for a time t with two different forces. So here we have box 1 is mass m being pushed with 3F, and then box 2 is mass 2m being pushed by force F. Identify the box system by circling the objects inside the system with a dotted line. All right, so this one right here is just the box. That's the only thing in the system there. And for this other system, it's a separate system. It's also just the box. So two separate systems, each of them just consisting of our box. Part A says identify the box, or excuse me, part B says the dots below represent the two boxes. Draw free body diagrams showing and labeling the forces, not components, exerted on each box. Draw the relative lengths of all vectors to reflect relative magnitudes. Identify the forces there. All right, so 1, 2, 3. We know we got a force of gravity on this box right here. And so 1, 2, 3. I just do it 3 long. It's kind of up to you. I'll draw a normal force right there. It's got to be equal and opposite since it's not accelerating in the y direction. And then I'll do 1, 2, 3, 4, 5, 6. And I'll call this force applied. So that is on the first box there. Second box is twice the mass. So it's going to have twice the force of gravity on it. So since I drew this one 3 long, I've got to draw this one 1, 2, 3, 4, 5, 6 long. And likewise, then the normal force to cancel it out will be 6 long. 1, 2, 3, 4, 5, 6. So normal force is up there. Now the last thing is, remember, this is 3F and this is F. So this is only 1/3 the force. Here I drew it 6 long, so here I just got to draw it 2 long. So that's the applied force in that case there. So the next thing they want you to do is say the forces that are external to the system include, well, it's all of them. It's the normal and the force applied and gravity. They're all external to the box. So that's kind of a ridiculously simple question. All right, next one here. It says, Part C, sketch a graph of the net external force versus time for each box on the same axis by using 2 different colors and providing a key. Okay, I can do that. So let's just say here box 1 was the 3F, so I'll just go 1, 2, 3, 4, 5, 6 up, kind of like I did on the other one. And that force is constant. So it would just be that force the whole time there. And this is the force 1, I'll call it, in purple there. So the other one is 1/3 that amount. So the force on box 2, if I drew this one 6 tall, for me it would only be 2 tall. And it's also constant, so it just comes straight across like that. I'll call this F2, the force on the second box there. You could have drawn this one all the way up here and the other one halfway through, whatever. As long as the force 2 only goes up, before I said halfway, 1/3 of the way of the other force there. So next thing, it says to do some quantitative analysis. So we're going to look at some numbers. So part D, use the equation for the area of a rectangle, area equals base times height. Write 2 equations, one with words and one with units for the area of the rectangle between the net external force versus timeline and the x-axis, the graph created in part C. So basically, they want to know the area of either one of these boxes. So we can just think of it as one here. So let's look at this. Let's do it with words first. It will be, height times base, or base times height. So force on our y times time on our x there. So our equation for the area is force times time. So that's our word equation. Well, we could also think about it in terms of units. So the area will be newtons for the force and seconds for the time. So what is that? We've already discussed what that means. That means that the area must be equal to the impulse, because impulse is measured in newton seconds there. But according to the impulse momentum theorem, what do we know the impulse is equal to? The change in momentum. So The area is force times time. That's impulse. That's change in momentum. So it's all of those things. So the area of the net force external versus time represents you can say impulse here or change in momentum. Each answer is acceptable there. Okay, so next part here. This is a little weird. So it says part E, re-represent the data above by creating a momentum diagram for each box on the same set of axes by using two different colors and providing a key. A momentum diagram represents the momentum of an object or system by showing the mass of the object as the width of the bar on the chart and the velocity of the object as the height of the bar. So I'll stick with purple being box 1 and magenta being box 2. So in the beginning here, neither box is moving, so they won't have any momentum. So I'll just do, it's just a line right there on the x-axis. And same thing for box 2. It doesn't have any momentum, so it's just a line right there. So this will represent the momentum of box 1, and purple will, and magenta will represent the momentum of box 2. All right. So now find the impulse implied to each one. So if we look at that, box 1, they're pushed with the same amount of time. So let's just make, 2 bars here represent the time or whatever. So box 1 is pushed on with 3 times the force. So again, I'm just going to go up 1, 2, 3, 4, 5, 6 here, just so you can see it. There, I'll fill that in. So that would represent the impulse. The force is my height and the width is my time there. So if that's box 1, then box 2 will only be 1/3 that force. So instead of 6 high, we'd only go 1, 2 high, like that. So the impulse is far less in this case for the second box there. So what about the box's final momentum? Well, these areas here, just like they did on the other graph, these represent the impulse on the box, so they also equal the change in momentum. If we start from 0, then the change in momentum will equal the final momentum. Because if our change is 10 and we started at 0, then our final momentum must be 10. So that means whatever the area of this box was, I've got to have the same area over here for my final momentum. Box 1, let's just say that a bar wide is its mass, or you could do 2 bars wide, doesn't really matter, just to keep it the same as over here. So if I do 1 bar wide here, 2 bars wide, let me do that. So I'd go 6 high. 1, 2, 3, 4, 5, 6. So this is the same basic rectangle as there. What about this other box? So box 2, remember, is twice the mass. So that means I drew this one as 2 blocks wide. That means I've got to draw the other one as 1, 2, 3, 4 blocks wide. But I've got to have the same areas over here. Here I've colored in 4 blocks. That means I got to color in 4 blocks over here. So I can only go 1 high there. So that is the same amount of, here's the impulse. That area of 4 blocks is the same as the area over here, which is the box's final momentum there. So notice that because it's got a bigger mass, which spreads it out this way, that brings down my final velocity. If I had the same mass as the other one, my momentum would be higher here, or my velocity, would be higher there. So finally it says, part F is the work done on the first box while speeding up greater than, less than, or equal to the work done on the second box while speeding up. So, well, let's look at it. Remember this, that work is equal to change in kinetic energy. Let's look at our speeds here. On this box, I'm 6 times the velocity there. I'm 6 boxes high. So when we go to do this, 1/2, box 1 is mass, and it's going to have a velocity of 6, let's say, squared. So 36 times 1/2 will be 18 m there. My second box here, its velocity is only 1 comparatively. So again, they might not actually be 6 meters per second or 1 meters per second, but it's a proportional problem here. So 1/2 times, 2m, but only 1 squared. So when we do that, we see that we get far less energy there. So that means that the work done on the first box is greater than the work done on the second box. And then last part, it says, is the impulse given to the first box while speeding up greater than, less than, or the same as the impulse given to the second box? So here's the thing, they had the same time, but box 1 had more force. So that alone makes it pretty clear in that case, since impulse is equal to force times time, same time but a greater force on box 1.